So the first problem was about pseudo-random sequences, that is the pseudo-random sequences that you get from using a shift register and feeding back some taps. Okay. Actually, I think I should not have mentioned autocorrelation, then everybody would have got it. That seems to have confused people. So by demultiplexing, we get two streams at half the rate, and I've used different time indexes m and n for the input and output because they are at different rates. Okay. So, and I said this is pretty obvious. This is just the definition of demultiplexing. You get the even stream in one and odd stream in the other one, and X itself is generated as a pseudo-random sequence. So it is, in this particular case I am taking PRBS 7, so I take the 6th and the 7th previous inputs, XOR them and form the next input, next value of X. Okay. So now if Y1 and Y2 are pseudo-random, they have to follow the same equation. Okay. They can be inverted in logic or they can follow the same equation. Or another possibility is, I mean, this also gives you, if 6 and 7 give you, 1 and 7 also give you. Okay. This we discussed earlier. If you have tap numbers, you have the last tap. If for PRBSN you have the last tap, and let's say you have N1, and then N minus N1 and N also give you the stuff. Gives you the pseudo-random sequence, but in a different order. It's a time reverse version of the same pseudo-random sequence. Okay. So, but anyway, the idea is to prove that it will fall into one of these categories, right? So let's take Y1 of M. We would like to prove that, for instance, Y1 of M is Y1 of M minus 6 and M minus 7 XOR together, right? So Y1 of M is X of 2M, which is the XOR of X of 2M minus 7. Okay, this comes from the generating equation for X, this one. And Y1 of M minus 6 is what? What is Y1 of M minus 6? X of 2M minus 12. That's all, right? And Y1 of M minus 7 is X of 2M minus 14. So if you look at it, this has a delay of 6 and this has 12 and 14. So we try to express this as we try to relate it to previous input. So X of 2M minus 6 itself can be written as X of 2M minus 12 XOR X of 2M minus 13. Is this okay? Is this okay or no? No? So X of N is X of N minus 6 and X of N minus 7. So every X at N is XOR of the ones before 6 bits and 7 bits. So X of 2M is an XOR of X of 2M minus 6 and 2M minus 7. So X of 2M minus 6 itself is X of 2M minus 12 XOR X of 2M minus 13. Similarly, what is this? If you have to express this as a function of past inputs. Okay. So this is X of 2M minus 7 and this is X of 2M minus 6. So what does this give you? 0. Why? Yeah, I mean even this part gives you 0, right? So X of 2M minus 13 XOR X of 2M minus 13. So this gives you 0 and 0 XOR anything else is the same number. Okay. So this is simply X of 2M minus 13 2M minus 12 2M minus 14, which is Y1 of M minus 6 Y1 of M minus 7. So it comes from the same generating equation, so it is also the same pseudo-random sequence. Okay. Similarly, you can do it for 2M minus 1, I mean 2M plus 1, Y2 also. It comes out exactly the same way. You get two terms which cancel out. Okay. So it turns out that if you demultiplex a pseudo-random sequence, you get the result is also pseudo-random sequence of the same length. Some of you have written that the period is half of the before. First of all, the period is 127, so it can't be half exactly, right? So it is, the period is, this is the same, it is also 127. Each of these has a period of 127, it's exactly the same pseudo-random sequence that you get. Okay? Now this proof is only for sequence of length 7, but it is true in general. Okay? So if you demultiplex a linear feedback shift register output, you get 2 more similar sequences. Is this okay? Now there is also the other relationship between Y1 and Y2. Now actually this is not, this is independently of whether it is PRBS or not. In fact, it's only related to the fact that the input has a period of 127. Okay. Now, so X has a period of 127. So let's label the time index N 0, 1, 2 up to maybe. So here it completes a cycle and then it starts on another cycle. Okay. And 254th one is the same as 0 and so on. Okay. Now if you look at Y1, so this 0 is the same as 127 is the same as 0, 120 is the same as 1, etc. Right? So this is the same as 126. Is this okay? So what do we get? Y1 we get 0, 2, 4 and so on. So finally we get 126 and we get 128, 130, etc. all the way up to 252. Now this 128 is the same as 1, okay, 3, so on. Is it okay? So basically this, the numbers I am writing here is the index of X that appears on Y, that comes to Y. And if you look at Y2, it starts as 1, 3, 5, you get 125 and then you should get 127, 129 and so on. And 127 is the same as 0, 129 is the same as 2. Okay. So what's the relationship between Y1 and Y2? It's a shifted version. Okay. And what is the shift? 64 or 63. I mean, it's 64 one way or the 63 other way. Okay. So Y1, Y2 of M is Y1 of M minus 64. Is it okay? Yeah. Yeah, that's true. I mean, it's just more difficult to do that. That's all. Okay. So yeah, I mean that can also be done. But actually, I saw some of the proofs. They looked. I couldn't understand any of them. So, but yeah, it can be done. I mean, you have to take the summation over 127 bits and show that it's 127 when they are overlapping, and when it's not overlapping, it's -1. So that doesn't show that it's the same pseudo-random sequence, but it shows that it has a white noise-like property. Okay. So in this case, it's not just that; it is even stronger. It's the same sequence that you get. Yeah, that's why I said if I had not mentioned autocorrelation in the problem, I think it would have been, life would have been easier for everybody. So Y2 of M is Y1 of M minus 64. This, I point out, is not really related to the pseudo-random nature of the sequence. It's just that it has a period of 127, okay, or some odd number. And so this again turns out to be a general property. So you, let's say you have a PRBS N sequence. Also, there can be other kinds of pseudo-random sequences. What I write here relates to the sequences I get from the linear feedback shift register structure. Okay. So PRBS N sequence, I demultiplex into 2, demultiply by a factor of 2, I get each of the demultiplex sequences PRBS N. Okay. And also the output sequences are shifted versions of each other. Okay. And the amount of shift is what? 2 to the n minus 1. So this is the amount of shift. Okay. And also let's say you have a pseudo-random sequence at low speed at 500 megabits per second, and you want to get a pseudo-random sequence at 1 gigabits per second. What can you do? I have a low speed pseudo-random generator. I want to get a high speed pseudo-random generator without actually making the linear feedback shift register at the higher speed. What can I do? So I can, if I have, let's say, PRBS 7, then I take the shifted version of it, I shift it by 64 bits, and I multiplex the two, I will get pseudo-random sequence. That's the inverse of this. If I have y1 of m and y2 of m equal to y1 of m minus 64, I multiplex the two, I would have got the pseudo-random sequence. So that's one possible way of making high-speed pseudo-random generators using low-speed generators. It may become difficult to do it at very high speeds because you have, especially with a longer pseudo-random length, maybe you have a large number of flip-flops and you have to close the feedback around those flip-flops at a high speed. So instead of that, if you have a low-speed generator, then you can keep shifting it, multiplex it, then shift that, multiplex it, or you do some things like that. Okay. In fact, you don't have to have multiple shifters. If you have a low-speed generator and a multiplexer, you can do it with shifting it at the input. So you can also generate high-speed PRBS by multiplexing shifted low-speed PRBS. And the fact that when you demultiplex it, you get the same pseudo-random sequences is also useful because I said you use pseudo-random sequences to test the circuitry. So one way is, for instance, the pseudo-random sequence, the way we generate it, it contains all possible 7-bit combinations except all zeros, right? So in a way, you are putting the circuit through a test of all possible bit patterns of 7-bit length. Now, if you pass it through a demultiplexer, every point in the demultiplexer, not just a 1 to 2 demultiplexer, let's say you make a tree of 1 to 2 and then 2 to 4 and so on. So every point in the demultiplexer will have a pseudo-random sequence. So every point will get tested in the same way. It will go through all possible bit transitions. So it's a useful practical result. Yeah. Yeah, that's correct. So how would I get that? I have only y1 of m. I have a low speed. I mean, this is going back this way, right? So I have y1 of m. How would I get y1 of m minus 64? I pass it through 64 flip-flops clocked at the clock rate. Okay. So I have this and I have a delay. This delay is z to the minus 64 or 64 flip-flops one after another. I will get a delay of 64. I multiplex the two, I get the output. Huh? Oh, the advantage is you have a low speed generator and you get high speed from that. Yeah, that's true. So let's say we have a serializer, deserializer system and you already have a multiplexer in the system. Okay. So maybe your system, your transmitter consists of a multiplexer. Let's say 64 to 1 multiplexer, and then you have an equalizer or a driver. So this is your transmitter. And let's say you want to put a pseudo-random signal on the link. One thing is you can make a high-speed PRBS generator and connect it here to drive pseudo-random sequences. Instead, you already have the MUX. So what you can do is, if you can make a low-speed generator, shift it appropriately and apply it here. Okay, and typically you have some other digital circuitry in this part, so you can use that to do a lot of this. So low-speed generator consumes less power, but of course it has more flip-flops, so it can potentially consume more power. But you are using the part of the same hardware, especially the high-speed hardware. So that's the advantage of that. Any questions on the first problem? The second was what? The latch, right? Yeah. So this is again somewhat simple. Although some of you have confused time and frequency domain in this. And the input is a unit step, or I mean it's a step of strength delta V. So it's very clear what happens. You get a current Gm times delta V times U of t, that is the unit step, right? So the output will ramp up at a rate Gm times delta V. Okay. So if you start from time 0, this is the equation of the output, sorry, by C. Okay. So at the end of time period t, the amplification is Gm by C times t. So the next one is the same circuit, except it is from 0 to t by 2, it is like this, and from t by 2 to t, it looks like this, right? Is that okay? So the initial part is the same up to t by 2. So at t by 2, the voltage across this is Gm by C times t by 2. After that, the input is detached from this, and whatever is the natural response of the circuit is what is followed. Okay. What is the equation governing this? So you have to use current, Kirchhoff's current law at this node. So the current flowing out of the transconductor is Vc times Gm, and that is equal to the current flowing through the capacitor, which is C times the derivative of the voltage. Okay. And the solution to this is a rising exponential starting from the initial condition. Okay. So in this particular case, this initial condition is at time t by 2. Okay. And this is, so you can, I think this is a first order solution, you can solve it quite easily. So at the end of the clock phase t, you get, so the first one has a linear dependence on Gm by C times t. The second one has a factor which has a linear dependence. The factor is in fact is smaller than this, but it has an exponential dependence as well. So for fairly small values of Gm C by times t by 2, this will be, the gain you get from this is more than this. What is the value of Gm by, what is the value of the Gm by C times t for which this is greater? The second one, the exponential stuff. Huh? 2 ln 2 or ln 2. Oh yeah, this is 2 ln 2, that's right. So this factor has to be 2, so the exponent is ln 2, okay. So the exponent is half of this. So for a very modest gain, if you are trying to get a gain of 2 ln 2, which is what, 1.4 or something, you get a larger gain with the positive feedback latch. This is why you use it to resolve digital inputs. Okay. The reason you can't use it for amplifiers is once it starts blowing up, it can reach saturation. But there is a way to control it and use it, and there used to be a class of receivers which are not very popular today, but they can be still used. They are sometimes used, known as super regenerative receivers. For a radio, you receive a small signal and you have to amplify it by a lot. So especially in the old days when gain was limited, you would use these things. So you temporarily put it in a positive feedback mode, so that you set up the initial condition with the input signal, and then you let it blow up for some time, then you reset it, you do it again. So that way you get a large gain. So that's known as a super regenerative receiver. What was the third question? Oh yeah, equalizer. Yeah. So equalizer for precursor and postcursor ISI. So one of the channels is 1 plus half Z inverse. This has postcursor ISI. The other channel is 1 minus 0.5 Z inverse. Sorry. Yeah. 0.5 plus Z inverse. So this is the cursor, this is the precursor ISI. Okay. The equalizer for this, I'll write down the answer straight away. I think all of you have got it right. It is 1 minus half Z inverse. Right. And what is it for this? Huh? Minus pi half plus Z inverse. Huh? What is it? Minus half plus Z inverse or no? No? 4. Why? Why did you get that? This is the, in this case, this is the channel. This is the equalizer. Okay. What is the result? The result is 1, 0, minus 0.25. Okay. And what is it in this case? This is the channel, and this can be the equalizer. So you get minus 0.25, 0 and 1. Okay. I think you have done some normalization incorrectly, that's why you get that. Is this correct or no? No? You will get 0, right? How will you get the cursor as a Z inverse? Huh? Oh, I see. Why? I thought I had clearly said that the peak is the cursor. So anyway, I think you get the same answer. But, huh? Yeah, you have to scale it up because, I mean, the cursor is so small. Yeah, but, okay, what is the equalizer you got? 2 minus 4, it's the same equalizer, right? It is this times, no, whatever it is, it's the same equalizer. This times minus 4, isn't it? So you will get the same thing. I mean, it is scaled up unnecessarily, that's all. So anyway, the bottom line is, where is the 0 of this? This is at z equal to half. Actually, some of you have goofed this. This is very strange. After getting to this point, you have goofed where the 0 is. But, and here it is at z equal to 2. Okay. So this is inside the unit circle, this is outside the unit circle. Again, this is for one particular channel, but it is in general true that to equalize post-cursor ISI, you need zeros inside the unit circle. Or if you are using continuous time equalizer, you need zeros in the left half plane. So to equalize precursor ISI, you need zeros in outside the unit circle, or if you are using continuous time equalizers in the right half plane. So I mean, that's just the way you design it, right? So actually, we have not discussed one type of equalizer which can only do post-cursor ISI, right? We have not discussed it. That's a decision feedback equalizer. So in combination with that, you can use an equalizer that does only precursor, that corrects only for precursor ISI. So in that case, you would have a right half plane or a left half plane 0. It's just to know like what you get, right? So for instance, I mean, that will give you an idea of the range of the coefficients. So if you see a response and you see a lot of precursor, so you know that you have to make some circuit that gives you right half plane 0. So left half plane or inside the unit circle to cancel precursor ISI and post-cursor, thanks. Post-cursor ISI and right half plane or outside the unit circle to cancel precursor ISI. Okay. So this is just something to keep in mind, and if you want to cancel both using a linear equalizer, you will need zeros in the left and right half plane. It will give you factors of this type. For instance, if you multiply, so in case of the continuous time equalizer, you will have a 0 here and a 0 here. Okay. Finally, the fourth problem, the echo canceller. Again, this was not a conceptually complicated problem, but I think some of you have lost track of the signals here and there and made some mistakes. I had mentioned this early on in the first or second class, the idea of an echo canceller. If you are communicating over the same pair of cable both ways, you need an echo canceller. And the easiest example is your telephone. You have a single pair of wires and you talk both ways through it, but you don't hear your own voice through your own receiver, right? You hear the other person's voice and the other person hears your voice. And the way it is done is to cancel the contribution of your transmitter coming into your receiver. Okay. So let's say this is the first transmitter and it's trying to switch a current I0, and of course other things are connected to it. So each of this is a 100 ohm transmission line, but anyway that is irrelevant because it is terminated perfectly. Okay, so it is connected up like this, and if you just so this is the transmitter part. You have a transmitter connected at either end of the transmission line, and then to receive the signal coming from this side, you have a receiver. I have AC coupled it to not disturb the bias of the transmitter, and let's say the receiver is some differential amplifier, in this particular case using op amps. And actually I defined the receive signal to be like this. I mean, it had no significance actually. To get the non-inverting gain I had to define it the other way, so that's a trivial. Any questions? Or okay. So, and I have exactly the same thing on the other side. Okay, and the values were chosen so that on either side you get a perfect 100 ohm termination. Okay, this was 125 ohms and this was 500 ohms, and it's a symmetrical problem, so you can ignore one side and calculate the result from the other side. For echo cancellation, the equivalent circuit is, so looking in here you have a 100 ohms basically, 100 ohms to ground, right, in the signal picture. So if you apply VTX1 and if you assume full switching, the voltage that you get across this, let's say V1, let's say this side is not activated, the right side is not activated. Okay, for echo cancellation I am trying to see what comes back through this loop. I am trying to cancel it out. Okay, so what is the voltage V1? Huh? 15. What? No, okay, it's basically, yeah, it is, I0 is given as how much? 20 milliamps, right? Huh? So it is 20 milliamps times the total impedance connected to each side. How much is that? 50 ohms. Yeah. Is it clear to everyone that it is 50 ohms that's connected? So you get 125 ohms and 500 ohms in parallel. The parallel combination is 100 ohm. So the situation you have is, you have a transmission line terminated by 100 ohms and the impedance is 100 ohms. So it's like connecting 100 ohms from here to ground. Okay. So essentially I have 100 ohms to ground here. Well, I mean small signal wise it is ground, right? Not small signal wise, rather incremental signal wise it is ground. Meaning if I apply a voltage between this point and ground, a current flows in that says that the impedance is 100 ohms. So I have to connect the impedance between that point and ground. Okay. So 20 milliamps times 50 ohms times the sine of VTX1. Okay, that's what appears here, assuming full switching. Now what is the current that flows into the receiver because of this? Huh? By 1000 if you look at it differentially. Okay, this is V1 is the voltage across this. So the incremental current flowing here is that divided by 1000. Okay, is that okay or no? So this I is 20 milliamps times 50 ohms times sine of VTX1 divided by 1000. Okay. So if I cancel off this part of the current, I will be fine. Differentially it is 1000 ohms. From each one to ground it is 500 ohms. So I have this. Okay. So I can measure the impedance by connecting a 1 volt source here. So if I do that, the current that flows is 1 volt by 1000, right? Is that okay or no? If I measure it differentially, each end will have an impedance of 500 ohms to ground. Okay. Now that will create, what is the output that it will create? VRX1. Huh? 1 volt. It's the same thing. I mean, this times 1000 is the differential output. So each of this is 500 and 500. And how would I cancel it? How do I cancel this? I want to make VRX1 equal to 0. But of course, the transmitter should be operating. So this is pushing in some current through this path, and I can use the virtual ground of the op amp to do current summation. So that's what I do, and in that current summation, I'll provide exactly the opposite current. Okay. So this diagram is getting more and more messy. Okay. Now I apply, firstly, which polarity should I apply it in? Which side should be plus? In this case, I think this is the right one, because when it's plus, the current that is flowing in here should be drawn out of this one. Okay. So this is VTX1. I mean, this may be the opposite sense of how the diagram was drawn, but that's okay. As long as you know how to get the sign, that's fine. And how much is the current that I want to put there? So basically, the output that comes out just because of the lower pair, if you ignore the top one, is what? The differential voltage VRX1 because of the bottom echo canceller. What is that thing? Let's say this is I1. I1? So it's I1 times 500, right? Is it okay? So I want to, and the VRX1 because of, this is because of the echo canceller. Actually this is minus. And VRX1 because of the transmitter is I0 times 50 times sine of VTX1. Okay. And I want this to cancel this exactly. So I'll make I1 equal to I0 by 10. Okay. Is this clear? So essentially this is the transmitter is pushing some current into these resistors. I cancel it off by drawing an exact amount of current. So the connection has to be in reverse polarity and the magnitude has to be whatever current is flowing through these 500 ohm resistors. And I can do that by making I1 equal to I0 by 10. Okay, so this is 2 milliamps. What about the WL of this? So if it is fully switching for any input voltage, I don't care if the input is perfectly rectangular. But it is not rectangular. In fact, I want the waveform here to match the waveform here, not just the settled values. So I need to make, if this is W by L, I should make this 1/10 of W and L, so that the current densities are the same and the waveforms that are produced by the top transmitter is the same as that of the bottom transmitter. Is it okay? Fine. So I1 is I0 by 10 and W1 is W by 10. That's all that's there to it. Yeah. Yeah, okay. I mean, see, the way I have defined it, even VRX1 is minus of this. Yeah. I mean, that's because VRX1 is defined like this. I mean, that's just a kind of oversight, but there is a sign inversion in both the receivers, okay? If whatever voltage I have here, I get the opposite here and I also get the opposite on the other side. But that's not a significant thing. Now, what is the receive voltage amplitude once the echo cancel is working and I have VTX2 applied to the second transmitter? 1/10 of what? See, it's a symmetrical situation and this transmission line is as though it is not there, right? So this V1 or rather VRX1 because of VTX1 without the echo canceller was this much. Okay? So because of VTX2 it will be the same thing except it will be sine of VTX2. Is that okay? So you get 1 volt sine of VTX2 at the receiver. So whatever you transmit from here, it appears here, and whatever you transmit, sorry, not here, it appears here, and whatever you transmit here appears at Rx1. Okay, and the Tx1 contribution is cancelled by the lower pair. Tx2 contribution is cancelled by a similar pair that is connected to, that should be connected to these points. Okay. How are the? Yeah, like this. Yeah, so what are the practical problems with this? Can we do this? From this the cancellation is exact. What are the potential issues? Op-amp should, but okay, firstly it may not be an op-amp receiver, but yeah, it doesn't have to be an op-amp receiver, that's just a schematic, right? I could use a differential pair and do similar kind of cancellation. So, op-amp, if it is an op-amp based thing, then it has to work at high frequencies, but it doesn't have to be op-amp based, it's just like one way of doing it. Then, yeah, resistor variations, there will be a random mismatch between resistors. Is that the only problem? So there will be random mismatch, but the important kind of mismatch we have to be worried about here is this side, the left side is one chip and the right side is a different chip. Now this whole scheme relied on looking at 100 ohms into this transmission line. Okay, that means that all of the resistors on this chip will present a 100 ohm impedance. So mismatch between two different chips is even more. There is mismatch on this chip, mismatch between this chip and the other chip. And finally, the most serious thing is really the transmission line itself. It won't have an exact 100 ohm impedance. The impedance will have imaginary part as well. The transmission line impedance may have imaginary part. In any case, you will have capacitive loading from the other side, loss in the transmission line and so on. So there is no way you are going to see only 100 ohms here. You will see some real part, you will see some imaginary part. Okay. So that is the most serious problem, but the other ones are also problems, mismatch and so on. So this kind of thing is good only for first order cancellation. Okay. So you do first order cancellation like this, and after that, especially because the impedance looking in here is imaginary, the echo cannot be, the part of Tx1 that comes to Rx1 is known as the echo. The echo cannot be just a simple ratio. In this case I said Vrx1 is Vtx1, sine of Vtx1 or something. It won't be just a ratio. It will be Vtx1 going through some filter function. Okay. So just like you do for adaptive equalizer, you have to have an adaptive equalizer here to cancel out the contribution of Vtx1 in reality. Yeah. Yeah, what about it? Yeah, that's true, and that can be made sure of. I didn't show any details of the op-amp, like I have not said what is the common mode voltage of the op-amp, but we can adjust it so that it is the same. Okay. Yeah, that's true, and if it's not the same, there will be some mismatch because of that as well. So firstly there will be random mismatch because you can't just match two circuits exactly, and some systematic mismatch maybe because you couldn't match the bias conditions exactly. But the more severe practical thing is the impedance is not real, so you will get a filtering action in the echo. So you can use this for first order cancellation, so that what you receive on this side is predominantly from this transmitter. And after that you can have an adaptive equalizer you can use an adaptive equalizer to do anything. So in this case you can use it to cancel off the echo. Okay. So for instance you have, I will show it schematically. So let's say you have transmitter 1 transmitting onto a transmission line. This is the output impedance of the transmitter. It is assumed to be matched on both sides. Okay. And this goes to the receiver. So this goes to the receiver, and you try to cancel the transmitter 1 contribution as much as possible, okay, by using a hybrid like this. So that comes out of an identical transmitter, or I will just show a kind of dotted line. But in reality what you have to do is you have to have additional cancellation through a filter, okay. Because the feed forward, the echo has a filtering operation, you have to essentially mimic the same filter and then subtract it out. Huh? Yeah, that's true. I'm just showing it as this thing. So, and many times it is implemented like this because you get some analog cancellation, and then after that the part that you have to cancel is small. You don't have to cancel a large signal. So in this case, I mean, when I draw it like this TX1 is like the echo canceller that was in the midterm. So it is this memoryless echo cancellation. So it cancels a large part of the signal, but leaves a small part behind that is done by the filter. So essentially the signal provided by the filter is small. So that's a practical way of splitting it. But yeah, from a purely signal processing standpoint, you can just say that you will find what the echo transfer function is and subtract it off. That's all. Yeah? Yeah. Yeah. So essentially this side receiver. So I have the transmitter. So some part of this is coming to this receiver. So I deliberately add another part, and this signal is correlated to this signal. I mean, it's the same as that signal. Okay. Is that what you are asking? Yeah. Oh, yeah. I mean, usually, well, if you have that, then you will have even bigger echo problem. But typically, when I said multiple transmitters, I assumed separate transmission lines for each case. Okay. So yeah, potentially you can do that also. You can just dump all the data onto a single line. In which case, there will be a lot of. We are talking about near end crosstalk. In this case, it's not. This is like an extreme case of crosstalk, right? You have connected the two lines together. So this is an extreme case of near end crosstalk. So you will have to cancel all that out also. But typically, you will have different lines at higher speeds. Okay, let's stop here. Any questions on any of this?